So today we're discussing bisects, medians, and altitudes. So we're going to start out with some vocabulary and some theorems. So we have perpendicular bisector. A perpendicular bisector of a side of a triangle is either a line, a segment, or it could even be a ray. And it passes through the midpoint of the side and is perpendicular to that side. So it makes a 90-degree angle. So then we have some theorems that go along with these. So there are two of them. So the first one is 5.1. Any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. Okay, so what's that saying is here, if I have the segment CD, this perpendicular bisector that goes through there, it's the same distance from here where it crosses to C and where it crosses to get to D. They are the same distance. So then 5.2 says any point equidistant from the endpoint of a segment lies on the perpendicular bisector of that segment. So it's taking exactly what we said for 5.1, it's just flipping it. Okay, so here we knew that it was a perpendicular bisector. Here we know that the distances are equal. Okay? So in the next piece that we have, sorry, let me adjust there just a little bit. When three or more lines intersect at a common point, the lines are called concurrent lines. And their point of intersection is called the point of concurrency. So when we have three or more lines that are intersecting, that point where they cross each other is the point of concurrency. The point of concurrency of the perpendicular bisectors for a triangle is called the circumcenter. Okay, so we always have three lines that would intersect. So we would have three perpendicular bisectors. Where they intersect is that circumcenter. And then we have some information that goes along with that. So circumcenter theorem. The circumcenter of a triangle is equidistant from the vertices of the triangle. Okay, so here's our circumcenter. So it's the same distance from all of our vertices. Okay, so an example of that, if J is the circumcenter of ABC, then AJ, BJ, and CJ are all the exact same length. Okay? Alright, so let's look at some more theorems here then. So now we have 5.4. Any point on the angle bisector is equidistant from the sides of the angle. Okay, if you remember, an angle bisector means that it cuts it into two equal parts. The angle is cut into two equal parts. Okay? And then 5.5 says any point that is equidistant from the side of an angle lies on the angle bisector. So again, these are just inverses of each other, depending on what information you know. The angle bisectors of a triangle are concurrent, and their point of concurrency is called the incenter. Okay, so now if we have angle bisectors where those meet, we call it the incenter of a triangle. So our incenter theorem. The incenter of a triangle is equidistant from each side of the triangle. Okay, so we're right here. So we're looking at angle bisectors. So I have an angle bisector here, I have an angle bisector here, and I have an angle bisector here. And where they meet, right here in the center, we'll call this K. I know that's kind of hard to see, but that is your incenter. Okay, where those angle bisectors meet. Alright? Like I said, there's a lot of vocabulary today, so just bear with me. So next is the median. A median is a segment whose endpoints are a vertex. Okay, so a vertex right here of a triangle and the midpoint of the side opposite of that vertex. So here's the midpoint. So it's where those meet. Every triangle has three medians. So the medians of a triangle also intersect at a common point. The point of concurrency for the medians of a triangle is called the centroid. Okay, so where we have all three of them meeting. So I could go ahead and draw the rest of these. And that point right there would be our centroid. Alright, so then we have a centroid theorem. So let's scoot up here. Our centroid theorem. The centroid of a triangle is located 2/3 of the distance from a vertex to the midpoint of the side, opposite of that vertex on a median. So what that tells us, if I have this segment here, BF, okay, so if I have that segment, then I know that BL is going to be 2/3 of that whole distance. Or we could also write it this way, BL equals 2/3 times BF. Okay, 2/3 of this whole distance makes this piece. So that means this little one left, that's going to be 1/3. Alright, let's try an example with that one. Okay, so here's our information. So we have points S, T, and U that are midpoints of DE, EF, and DE, EF, and DF. So then we're going to find X, Y, and Z. So we're going to start out, let's start out with EU. So if we look back here to what it said, it's telling us this longer side equals 2/3 of the whole thing. Okay, so let's apply that over here. So EF, the longer piece is EA. So EA equals 2/3 of EU. Okay, EU is this whole piece. Alright, so let's plug in what we know. EA is Y. So Y equals 2/3. EU, we're going to add those pieces together. So 2.9 plus Y. And then we're just going to solve. Okay, I'm going to go ahead and write out the others before I solve that though. So let's look at DT. So the longer piece here is DA. So DA equals 2/3 of DT. DA is 6 equals 2/3. DT would be 6 plus this over here, which is 2x minus 5. Okay, and then I'm going to do the last one here. So we have SF, so AF. I'm going to have to scoot this down. AF equals 2/3 of SF. Okay, and we go back up here. AF is 4.6. 4.6 equals 2/3. SF is 4.6 plus the 4z. 4.6 plus 4z. Alright, so now we can work on solving these. Okay, so the first one is our EA. So we're looking at EA there. And we're going to be looking at this 2/3, because if you remember, we don't like to leave those fractions in there. So in order to get rid of those 2/3, we're actually going to be multiplying both sides by 3. So times 3 and times 3. Okay, we're multiplying both sides by 3. So we get 3y equals 2 times this 2.9 is 5.8 plus this 3 actually crossed out with that 3, that's why we're just multiplying by 2, so plus 2y. Okay, so then we've got to get our y's together, so we're going to subtract 2y. So we end up with 5.8 equals y. Alright, let's go over here to deal with the dA. So again, we're going to multiply by 3 on both sides. Actually, you know what, before we multiply by 3, let's simplify this here in the parentheses. So 6 equals 2/3. We have a 2x. We have a minus 5, a plus 6, so plus 1. Now we can multiply by 3. and it'll make it a little easier for us. 3 times 6 is going to give us 18. On the right hand side, our 3's cross out, so we're left with 4x plus 2. Subtracting 2 from both sides, 16 equals 4x. Divide by 4, we get x equals 4. Okay? Alright, let's move down to the last one. Here, again, we're going to multiply both sides by 3. So our 4.6 times 3 is 13.8 equals, these 3's cross out. So we take 2 times 4.6, which is 9.2, plus 2 times 4 is 8, z. So then we're going to subtract the 9.2 from both sides. We end up with 4.6 equals 8 z. So we divide by 8. We get z equals 0.575. Okay? Alright. A little bit more here. So now we're going to be dealing with the altitude. So an altitude of a triangle is a segment from a vertex on the line containing the opposite side and perpendicular to the line containing that side. If you remember when we were doing word problems, I had told you that an altitude, that's like when a plane is flying and it goes straight down to the ground. So the plane would be like our vertex, and then the ground is the other side, so it has to go straight down perpendicular. Alright? So every triangle has 3 of these. They intersect at what's called the orthocenter this time. Alright, so we are going to do a problem with this. So we're going to find the equation of the altitude for J to KL. So let's look over here. We have this triangle. The altitude, you remember I said it has to be perpendicular. So that's why we have this little box here from J down here to KL. So the first thing we've got to do is we've got to remember if they're parallel, slope is equal. If they're perpendicular, slope is negative inverse. Okay, so that's the first thing that we have to remember. So let's look here at our problem. L to K, the slope, we have our rise, the slope for LK, we went up 1, and then the run, we went 1, 2, 3 to the left, so that's a negative 3. So it's a negative 1/3. So then the slope perpendicular to LK equals the negative. So what's opposite of a negative? That's going to be a positive. And then the inverse, we're going to flip it over, 3/1. So this equals 3. Alright, so that's the first thing we need. Then we're going to be using one of our formulas. So since we have coordinates, we're going to use y minus y1 equals m times x minus x1. Alright, our point that we're using is point J. So we have y minus the y value, which is 3, equals m. Our slope is 3, so 3 times x minus the x value, which is 1. So we have all of that plugged into our equation. So then we're just going to distribute. So y minus 3 equals, distribute our 3, 3x minus 3. Then we're going to add 3 to both sides because we're trying to solve for y. Whenever you write an equation, we want to solve for y. So y equals 3x. And then these 3's cross out. So you're just left with y equals 3x. And that's your equation for that line that goes from J and is perpendicular to LK. Alright, that's all for today. If you have any questions, please make sure that you're asking those in class, and I'll see you in class tomorrow. Bye.